Our next speaker, Ricardo Rioda, earned his degree in Computer Systems Engineering from Tecnológico Nacional de México, Instituto Tecnológico de Tijuana in 2024. He is pursuing a Master's in Engineering Sciences at the same institution. In 2019, he competed in the National Physics Olympiad. In 2024, Ricardo participated in the Womanium Quantum Workshop, the seminar on artificial intelligence and quantum computing, and NEO 2024, presenting research of multi-class evaluation of vision transformers for industrial welding defection. In 2025, he attended the Numerical Methods in Quantum Information Science Summer School at the University of Massachusetts Amherst, and SPI Optics and Photonics in San Diego, California. He currently works in data science and ITJ labs. His interests include mathematics, physics, quantum computing, and machine learning. Ricardo continues to deepen his expertise in AI and data analysis to solve real-world challenges. I give the word to Ricardo Rioda.
Hello. Okay. Hello, everyone. I'm going to present our work titled Speaker Identification and Gender Recognition, a benchmarking study of machine learning and deep learning models. Okay, I'm going to start with the problem statement. The problem statement is that for speaker identification and gender recognition, these are very important tasks, for example, for authentication and also for surveillance. So for that reason, we want to make a benchmark for different classifiers and also for different feature extraction techniques. For example, machine learning versus deep learning, also MFCC versus Mel spectrograms. MFCC stands for male frequency substrate coefficients. It's just the representation is just a vector. Also, because there is a lack of standardized benchmarks for these tasks, so that's also the reason. Okay. For this work, we are using three public datasets. The first one is the Common Voice Mozilla dataset. It contains diverse voices. We are also using the Audio MNIs. It contains digit recordings from multiple speakers. We are using the RapDes dataset. It contains emotion-rich recordings with gender annotations. So we are using these datasets for their diversity, also accessibility, and they have also enough data for our benchmarking. Okay, for the state of art, there is prior work before ours. For example, gender identification using MFCC, also age and gender recognition using convolutional neural networks, speaker and gender recognition using deep neural networks, analysis and investigation of speaker identification, and the audio MNIs. So the differentiation of our work is that we make a benchmark for different classifiers and also different feature extraction techniques, and also for this task, for example, speaker identification and gender recognition. So the idea of this benchmark is not only to solve these problems, but then using these techniques, apply these techniques for other audio classification tasks. Okay, so the models that we are using XGBoost, CatBoost, ShuffleNet, RegNet, and a multi-layer perceptron. We are also using SwimTiny. It's a vision transformer model, VIT-Tiny, and a transformer multi-layer perceptron. Okay, so the features we are using two feature extraction techniques. We are using the MFCC. It captures short-term spectral characteristics, so the representation is just a vector. Later we are going to see a visual representation. Also, Mel spectrogram. The Mel spectrogram is an image, so we need to use image classifiers for this. Okay, for the training pipeline, first we have two tasks. We have the gender classification. This task is about identifying the speaker For example, given an audio, identify if it's female or male, sorry. Then speaker identification. This task is about, we have a set of speakers or individuals. We need to, given an audio, identify who is the owner of the audio. So we have 3 datasets: Mozilla, AudioEmenis, and Rapdes. And with these datasets, we create different variations of each dataset, depending on the task, and also the feature extraction. So this is the visual representation of the MFCC feature. It's just a vector. And then we have the MEL spectrogram. It's an image. So for this, we need, it's just a vector. We can use any classifier that receives as input a vector. Then for the MEL spectrogram, we can use it as an image. So we can create, and we can use any image classifier for this. So then we use the classifiers, a machine learning classifier, a vision transformer, a convolutional neural network, or a multi-layer perceptron. Then we train the classifiers and we evaluate them. Okay. And now for the experiments, we have designed three experiments. For experiment 1, the column technique is about the feature extraction techniques we are using. So in this case, we are using 2, the MFCC and the MEL spectrogram. The task is gender classification, and the dataset is Mozilla. For experiment 2, also we are using the 2 feature extraction techniques. The task is speaker identification, and the dataset is the Rapdes dataset. For the last experiment, this was designed to first run the 2 experiments and then decide which of the 2 features is better for us. And the task is gender or speaker identification. And the dataset, we are using the 2 datasets, Rapdes and AudioEmenis. So we are going to adapt each dataset depending the experiment. Okay, so for this table is about the training and validation and testing phases. So here, for example, for the 2 experiments, we create 2 variations of the first dataset. We can see in the first 2 rows, Mozilla and also Mozilla. It's the same experiment, but using different techniques, feature extraction techniques. We can see here. And then the same task and the same amount of samples. Then we have the Rapdes, for experiment 2, Rapdes dataset, using 2 different feature extraction techniques, the same task and the same amount of samples. For the last 2, we are using the Rapdes, but now for the gender classification task, using the best technique. In this case, we need to run the first 2 experiments and then decide which feature extraction technique we are going to use. And the last 2 datasets is AudioEmenis, but now for gender classification, and finally for speaker identification. Okay, so after running all the experiments, here this is the summary of the classification performance for all the experiments. So here we can see that, for example, in the dataset version, this column gives us information about the configuration of the experiments. For example, the syntax is, for example, gender is, for example, gender Mozilla spectrogram. The syntax is task, the dataset, and then the feature extraction technique. So for the gender Mozilla spectrogram, the accuracy we achieved was 94.66% using the ShuffleNet classifier. Then gender Mozilla MFCC dataset version, we achieved 88% of accuracy using the XGBoost. So then for the speaker Rapdes spectrogram, 94.88%. Also the ShuffleNet. Then speaker Rapdes MFCC dataset version, 87.50% using the CatBoost. So after the first 2 experiments, we decided to use the MFCC feature for the rest of the dataset versions, because even though we don't have we didn't achieve a good accuracy, the best accuracy using the MFCC feature, they have a faster prediction time. So for that reason, we decided we continue with the MFCC feature. So for the last 3 dataset versions, we use them. So for the gender rapdest MFCC dataset version, we achieve 100% of accuracy using a multi-layer perceptron. Then gender audio MNIST using the same feature, 99.88% multi-layer perceptron. And finally, speaker audio MNIST using the MFCC, we achieve a 97.71% of accuracy using a multi-layer perceptron. Okay, so now comparing with the state of art, remember that we have 3 datasets. We have the common voice dataset, the rapdest, and the audio MNIST. So for the first dataset, the current accuracy of the state of art is 98.57. So in our case, we achieve a 94.66. So in this case, we didn't surpass the state of art. Then for the rapdest, we achieve 100% of accuracy using a multi-layer perceptron. Finally, for the audio MNIST, we achieve a 99.88% of accuracy using a multi-layer perceptron. So in a few words, we surpassed the previous results of the state of art on rapdest and audio MNIST. Okay, in conclusion, using convolutional neural networks with MEL spectrograms, we achieve the highest accuracy for both tasks. Using machine learning models, using the MFCC feature, we achieve a faster inference prediction. So this is suitable for real time and also for resource limited scenarios. Also, the combination of MEL spectrum with convolutional neural networks. In a few words, we have the best accuracy. Using the MEL MFCC feature plus machine learning models, we achieve the best efficiency because it's a trade-off. So depending what you want, the best accuracy versus the faster prediction time. Also, we compare some transformer models. They show potential, but they underperform against the convolutional neural networks. So we surpass the state of art on 2 datasets, rapdest and audio MNIST, for the gender recognition task. For future work, we want to explore hybrid models combining the 2 features, the MFCC plus MEL spectrogram. Also, we want to investigate quantum enhanced techniques for feature extraction and also similarity matching, and improve performance and scalability in high-dimensional audio classification tasks. So that's everything. Thank you.